Okay, we've just completed the quiz. If you're watching the video later, we've had a few questions going on the quiz, and one of the questions was if you demodulate with the carrier rotated by 180 degrees, it flips the sign, but it just inverts the speech. If it was data, it would invert the data bits. So there would have to be an ambiguity resolver in there, because if it was supposed to be all zeros instead of all ones, you'd have to have a means of discerning that. But yeah, but in coherent communications, that's not an uncommon thing. One scheme is called differential encoding, and a differential encoding scheme, which is talked about in COM2, can resolve it on its own. But it has another downside of that. But these things have all been kind of dealt with over the years, right? It sounds like we ought to have a way of fixing that, and we do. So differential encoding can resolve that, and it can be applied at different levels in a communication scheme. It's called phase ambiguity resolution. So now that I've started that, this was the survey that I wrote. Hopefully I'll be able to post this tomorrow morning before I go down to Capstone Design. I can't post a video that I don't have processed, so this 30 gig thing, I hope that they can work that out. If I have to go to Canvas, I guess I'll have to go to Canvas for my videos. I mean, I like what I do, but if I've got to totally change my plan. It's nice to know we have an IT group that does that, though. They're working on it, and I impressed upon them. And they impressed upon me. I said, I'll remove videos, and they said that won't help. So that was encouraging. It's like I thought I could fix my own problem, but the good point was it's not like we're quarantined. I wasn't at my quota, and I guess nobody has a quota that's reasonable. So I thought if I have a quota of space, I'll pull something out of that space, and I'll put something back in. But right now they said if I pull that out of my space, somebody will just squeeze me over and take more of my space. So
nice hardware allocation.
Yeah. In the olden days, we used to have quotas, and you could interpret that when you had your system drive. You would put things on it, and you would have to make space to put more things on it, right? And that's what we have to do on our own machines or on our flash drives. But
so just dedicating a hard drive to each teacher feels bad.
Well, that's what quotas do on systems, though. I don't know. John, you're the one that mostly wants that I want you to hear this, because, and I'll post it on the website if I can't get it up, because it changes things around for me to get stuff up for you to watch. So at any rate, we're going to jump back over to where we left off. I've got phase lock loops lecture up right now, and we'll get into single sideband, then we'll get to frequency translation and mixing, which is showing up in the next COM lab. You didn't start with the radio boards yesterday, did you? The black boxes?
No.
It's in lab 4.
We haven't started lab 4.
Yeah. I walked in on Daniel when I was giving the candidate the tour of my lab, and he was in there playing with them. So I know he's been working with them, which is what I want him to do. And things are working, at least that's what he told me. So last time we were talking about Hilbert transform, and I just wanted to go back to the core basic is what is I outlined in red here is in the frequency domain. It applies a -j, so it's a 90-degree phase shift, and then it has this switching operation where it changes sign when you go through f is equal to 0. And we're now going to start using that in some analysis, in modeling. The time domain, which I highlighted in blue, was just simply to say it does exist, but it's not something we're going to use. Really, we're going to work with the Hilbert transform in the frequency domain to interpret into the time domain. So memorable Hilbert transform of a cosine is a sine. Hilbert transform of a sine is another 90 degrees of phase shift, so that takes us to minus cosine. Makes sense, right? And then so on and so forth. And then we had properties. One of the properties that we will be taking advantage of as we work our way along here is this one right here. If you have a narrowband signal and you had a high frequency signal C, like a carrier frequency, let's say, and you want to Hilbert transform the product of the two, it will be just the Hilbert transform of the high frequency signal, and the message signal will be left alone. So that's kind of a cool property that gets utilized, and this is kind of an example of that right here. If we're going to Hilbert transform a message like we've been talking about, a narrowband signal, a baseband signal times a carrier, and we have the opportunity to Hilbert transform the composite, it will be just the Hilbert transform of the high frequency signal, and the message will be left alone. So that could be useful in a modulator or in a demodulator application. So the next thing we're going to look at is analytic signals, and then once we get finished with that, then we'll jump back into chapter 3. I'm holding my head here for a second because I'm thinking about, remember the two problems on set number 5, the last two problems that I'm carrying forward to turn in next Tuesday. That second problem is analytic signals. So when you work those two problems, well, when I finish this part of the lecture, you'll be able to work those two problems, and that's where things are stopping also for exam 1. Does that sound good? So it'll take us through that point. And when I do the review on Tuesday, I'll say that's as far as we're going to go.
The exams next Thursday?
Yeah.
Okay.
So in effect, as soon as we get through this, I could draw a line in the notes and say anything above this is what we're doing on the exam. And I'll reiterate that next Tuesday. I didn't put the old exams up yet. And another thing, it's going to take disk space. Small though. I think probably it's going to let me squeeze that on. It's the videos that take up space. So I got to get that up there. So an analytic signal can be formed by taking the signal and then plus or minus j times the Hilbert transform of the signal. So clearly this is going to be a complex signal by the time I get done with it because I'm putting that j in there. And let's just see what goes on with the analytic signal. It's a very curious thing. It applies not just to single sideband, it applies to signal processing in general. It's probably one of the things that I like about the Hilbert transform is what this allows you to do. So first off, if you think of the analytic signal, and I guess I didn't say this could be plus or minus. You could have plus or minus in there, but in general, you can just leave it as it is.
What do you call it analytic?
It has to do with complex variable theory. And analytic signals or analytic functions, if I'm remembering right, and I told this to Colton the other day, right, how I took complex variables when I was an undergraduate from the math department.
You say a lot of things. It's
Yeah,
a lot to absorb.
Okay, sorry about that.
I was more trying to absorb this stuff than
Yeah.
your biography. Sorry.
Well, it's me though, right? Biography is a personal thing. So analytic signals are, and I don't really know if that's where it got its name from, but I have to think from my taking of complex variables theory that an analytic function, if I'm remembering right, see if I can remember my complex variable theory, what would I do today? I would type into Google, I would say analytic function. What does that mean? I'm not.
And by complex, you mean like the a plus bj?
Yeah, it's a complex valued function. When I say complex valued, you can put in a complex number and you get out a complex number. So it's complex all the way through. But an analytic function, if I'm remembering right, is differentiable at any point in some region that you define it to be differentiable. And why is that so significant? Because in a function of a single variable, the derivative is easy to talk about, right? You just differentiate it at a point, and if the limit exists, you know, as the delta t or whatever goes to 0, you say the derivative exists, it's finite. But in a complex domain, it's more complicated because if you're thinking of a space, how are you going to define the slope? The slope could be, you know, in the real axis, it could be in the imaginary axis, or it could be in any angle in that complex plane. So that's what's so special, that it can be differentiated in any orientation to get the slope definition. Mathematicians come up with cool ideas and then they want us to adopt them. Engineers, though, what is engineering made up of? I look at it very simplistically. It's made up of math, and what's the other core foundation of engineering.
Guts.
Well, but what's the other science field? We have math and physics, so we have to put those two together because physics is what governs our world, the way we understand it, and we only understand it within limits, right? But math can go way off in abstraction land and be totally intangible a lot of times, I think.
I always thought that it was always like a linear thing, not a convergence thing. Like there's math who finds it, physics who verifies that they can find that, and then we use what they find.
Okay, that sounds okay too. You heard that in what class?
Me.
Oh, it's your understanding. Because if you heard it in the math class and you heard it in the physics class, what's wrong with that? It's got a bias associated with that, right?
I don't like math majors.
Well, math is a powerful tool, and that's, the lecture I just came from on the power systems guy. He was talking about utility and microgrids and a lot of cool things about being green and mixing in other types of energy. He had no math. He just had pictures and neat drawings, and I thought, he cannot do this for very long. If he's talking about his research, he has to have math in there. And sure enough, then it started to be page after page of mathematical expressions, optimization things, and he was getting into how to build a microgrid. I took notes on my tablet, but it was optimizing battery sizing, costs of batteries, and with a bunch of constraints, huge number of constraints. I was using programming techniques called linear programming, which solve optimization problems. It's not a discipline within EE, but linear programming would be an optimization theory from CS or maybe math. Have you ever heard of linear programming? So we're trying to optimize with constraints. The only constrained optimization that you've done, and I'm getting really tangent off here, but I think it's one of the coolest things I remember from multivariable calculus, and I'm sure you did it because I did it, and I bet you did it too, and that was you had a cylindrical object like a can that holds some food. Do you remember the optimization problem was
Finding what the maximum of volume per ratio
of the surface area,
Yeah.
so that you could manufacture a can that had held the most material but yet minimized the most volume but used the least amount of material. I still think that's a cool problem to think about. Calculus let you do that though, right?
Yeah, I forget how though.
But you remember it though, that's the main thing.
I can Google it.
Okay, yeah, but I mean, would you have thought of that without your calculus background? It's like, there is an optimum.
They did the same thing, like the area of a square versus its perimeter.
Okay.
Like building a fence for like cheap or something.
Okay, and if you're buying a new house and you have to put a fence up, maybe you'll do that.
You can do that without calculus.
Have any of you ever had to do that, help somebody out? Build a fence in your
No,
backyard?
I have not met Throgmorton in his 16 watermelons.
Okay. Well, I had to do that for the fellow faculty member that joined the same time I did, and think again before you volunteer to help build a fence, especially if you volunteer to drive the post hole digger.
Oh yeah, no, those things are brutal.
Well, you don't know the kind of soil the property has, and drilling post holes in some parts of Colorado soil are like,
Yeah, you need the
wow.
one-man ones.
Pardon me?
You need the two-man augers.
Yeah. Okay, so you know what I'm talking about then.
Yeah, it sucks.
Okay,
My dad just gave me a shovel.
I've used the one, whatever the motion is, drive down, close it off, pull it up.
It's good for shoulder.
Yeah. Heavy duty stuff though. Okay, so we have an analytic signal. It's complex. We can define the magnitude of it, just like we can define the magnitude of any complex number. And it turns out this is related to the envelope that we've been discussing with double sideband and AM, the envelope detector in particular. And so they're related, and I'll get to be explaining that in an application a little ways down the road. And it's also got characteristics similar to single sideband when we look at an analytic signal. So if we take what the book calls Z sub P, which is the plus sign, and then we're going to have Z sub M for the minus sign, it's X plus J X Hilbert transform. We look at that. How do we make heads or tails out of it? We bring on the power of the frequency domain. So we look at it in the Fourier domain and say Fourier transform of x of t is x of x of f. Fourier transform of x hat of t is going to have to be x of f times the Hilbert transform frequency response, because after all it's just a filter, and that's the minus j signum of f. So you look at that and say, okay, I can bring that j outside with the minus sign, and that's going to, that's going to net out 1, right? J times minus j is going to net out to be 1. And then we just have the switching action, so we have the signum of f, and when we factor that out, now we get this nice, and this is this is problem number 5 on the homework. It involves this type of stuff. So that's a neat switching function that says when f is less than 0, we have 1 minus 1, which is 0, and when f is greater than 0, we have 1 plus 1, which is 2. So the big deal here is we get only the positive frequencies. I'm going to demo that to you in the Jupyter lab a little bit later here. It's very cool to think that we can take and we'll have a two-sided symmetrical spectrum. We'll make the analytic signal and blow away one side of the spectrum or blow away the other side.
So it's like a frequency spectrum rectifier.
Yeah, in a sense. That's an abstraction. If you want to keep that going, that's good. And the homework problem is a variation on this, but it's that basic idea. So we have the negative, it was n for negative rather than m for minus, I forgot, but minus sign, work through that, and it's the opposite of that. So this is the picture to think of it by. One-sided, positive side, negative side, two-sided, and then of course what we're going to be able to do in modulation theory, which is like coming up here next, is we can take that whole thing and shift it. So if we can shift it up and down in frequency on top of that, then we can create double side or single sideband, right? Because we can move that analytic signal idea and then move it up and down in frequency, and we'll be able to create just the upper sidebands, positive and negative frequencies, and just the lower sidebands and the positive and negative frequencies. So I'm going to do that, but I'm going to go for an interlude at this point and just go over to a discussion that I have in the notebook. Should I make the fonts bigger for this guy? Is that going to help him?
Yeah.
Switch it to presentation mode, and I guess I can shut off the table of contents there. So it's possible in MATLAB, Python, using scipy.signal. There's a function called Remez, which designs an equal ripple type of filter. But so signal.remez, shift tab, and it defines what you can do with, if I read all the help here, what I can do with the Remez function. And I use it in Scikit DSP-Com to design equal ripple, low pass, band stop, and band pass, or high pass, I mean. But here it also has a third type that you can put into it called Hilbert, and that's what we're looking at here. So we're going to use it to design a Hilbert transforming filter. And in Remez, what you get to do is you get to specify how many taps in your FIR filter, and you've all had 3205, so you know what an FIR filter is. You actually learned that in 2610, right?
Yeah, we didn't get to FIR in Circuits 2.
Okay. You learned it in 2610, though.
Yeah.
So this array is defining what are called the pass or the bands, the subbands of the filter. So we have a band that runs from 0 to 0.05 in normalized frequency, and then another band that runs from 0.1 to 0.9, and so on. And they're divided by 2, so that actually the highest band is sitting at the folding frequency, which would be 1/2. So that's why the 2 is over here. And then these are the weights to apply to the band. What do we want to have gain-wise in the response? We want to have approximately unity in the pass band, and then we're willing to, then we'd like to have a lower gain at the band edges. And I know in the Hilbert transform filter you can't make it perfect, but what we care about in the Hilbert transforming filter is the 90 degrees of phase shift. So here's a 31 tap, a 63 tap, and a 121 tap. So here I'm plotting the big one, the 121 tap FIR filter. Just proving to you that it exists as an impulse response. So it's causal. The first tap starts at 0 and then goes up to 120, so a total of 121 taps. And it's got an odd symmetry to it. And if you study FIR filters in detail, if you have an odd symmetric set of coefficients, that means you're going to get a 90-degree phase shift automatically. And here I've just went ahead and plotted the magnitude response of the filter. So 121 taps, it's very flat, it has a very fine ripple in it, and that's what Remez does. It gets you a equal ripple filter, small ripples, and then the gain drops off at the band edges, at either the folding frequency or DC. And then the phase is very linear, and that's a characteristic of a symmetric FIR filter. It has no group delay distortion. As a matter of fact, the delay of the filter is exactly half of the filter length. So that would be 121 minus 1 divided by 2 would be 60. So the delay is going to be 60 taps. Is that right? No. 121. I'm doing the math wrong.
So it's 100 taps?
Yeah, it's 121 taps, though, is what I
no,
made it.
Oh, sorry, I'm reading the wrong
Yeah.
plot.
I think it's 60 taps. I don't know why I've got 32 zeros in here. Let's just keep going, and I'll try to explain this, because right now maybe I only confused myself. You're not at all confused. So what I did here is I said, let's just see if this property, this filter, obeys the Hilbert transforming property. So I'm going to create a cosine, pretty low frequency cosine, but it's not so low frequency that it's below the band edge of the filter. Its normalized frequency is 0.05. So its frequency spectrum is going to sit right in here, which is in the passband of this Hilbert filter. So I send that signal through, and then I send the unfiltered signal through, but I have to delay it by the delay of the filter, because when you're doing something in signal processing with filters, and this is something, I'm tempted to go to the whiteboard, but it won't be captured. Maybe I can do it over here. If I want to build a realizable Hilbert filter, I'm going to have to send the on-Hilbert transform signal through the same amount of delay as the Hilbert filter introduces to make the comparison fair. So this would be x, and this will be x hat. I guess x hat, and put a delay on there, because there's a physical delay in creating a filter. That's just the cost of being able to filter as you introduce memory. At any rate, feeding that cosine wave in, I should get a cosine and a sine, because that's the nature of the Hilbert transform. So there it is. We see phase quadrature, and I just drew a line at the peak and the zero crossing, and that's phase quadrature, right? 90 degrees of phase shift would go from a peak to a zero crossing. So we see that's happening. What about the single sideband properties? So what I did here was I created a function that I called in Python analytic signal. So I have a parameter. I get to put in my signal. I get to put in the Hilbert transforming filter coefficients. And then I have a third parameter which defaults to creating upper sideband, which means I'm going to use the plus sign, or I guess I'm using the minus sign. And then, no, I'm using the plus sign for the upper sideband.
Backwards?
Yeah, it seems backwards to me, but I think I had to flip it over.
It's not upper, it's plus.
Yeah.
Upper, it's minus.
So at any rate, I've got both of those signs in there. So I've already defined this function, but
Was an audio file?
yeah, it's an audio file. Well, I'm going to use the male audio voice in here, so let's just verify that's still here.
Wall, dull green. The child crawled into the dense grass. Rye,
So then I'm going to create an analytical signal version of that speech using my function. And it's not perfect because of the fact that filter cannot do any filtering, cannot do proper filtering right down around DC. So when I'm bringing together the x plus j x hat, I'm going to not have perfect rejection around DC. So if I process that speech signal, notice it's got some residual down in the negative frequency, but by and large it is a positive frequency spectrum. Just kind of to add some weight to that, if I put lower in here and then run it, it flips it over. So it's roughly an analytic signal to within the limits of a realizable Hilbert transforming filter. So-
I guess for the negative signal.
Negative frequency.
Was the defects from the filter.
Yeah, that's right. And understand that we can't really listen to this signal, even though it's a baseband speech signal, because it's a complex signal. It's got a real and imaginary part. I can't send that complex signal through the speakers and have us listen to it. We could listen to the real part or the imaginary part, and then it's just going to sound like the speech. It's really not going to. It's not going to be impressive. It's not like if you're thinking you were going to hear what it sounds like to listen to a one-sided baseband signal, we can't do that because it doesn't exist. I mean, our ears process real signals, and as soon as we take the real part of the complex signal, then we're back to the two-sided spectrum again. But this will be useful for building up the single sideband signal. So that's kind of coming up next, putting it up on a carrier, and I do that here, but I'm going to jump back over to go through that development first off. So now we can use these ideas. So now we're jumping back into chapter 3. So this is our line of separation. We've just ended the analytic signal, which was described in chapter 2. And now we're jumping back into chapter 3 to continue the discussion of single sideband. So how do we generate single sideband? Well, simply on paper, one approach is to simply say we're going to create double sideband, which is what we get when we multiply the message by a carrier. So we have double sideband. And then we just need to have a magic filter that only passes the upper or the lower sideband. I call it a magic filter because what really is it? It's just a sideband filter. And you could just design that filter, but let's be more analytical about it and say, how can we get a mathematical representation of upper and lower single sideband? So the book goes through this kind of discussion. They say what we need is a filter like the red dashed line. The red dashed line, if we could have a low pass filter, so we'll pass the lower sideband, or I'll call it lower single sideband. And then we could take the complement of that filter and we'd be passing the upper sideband. But the book describes the design of what's called a phase shift modulator, which creates it through the use of the Hilbert transform. So it says, let's create a processing function that looks like our signum function. So we form a filter that has the red solid line here. So that's like step 1. And then we form another signum function that looks like that, and then if I superimpose those, notice that they each have gains of +1/2 and -1/2. That will synthesize that Hilbert transforming, or the filter that we're after. So now we can describe what that filter looks like. It looks like signum of f plus fc minus signum of f minus fc over 2. So to go about getting that filter then, let's just take that filter and apply it to a message signal. And that message signal in the frequency domain will be the double sideband signal. So this is the DSB part, and this is the filter. So this gets lower sideband filter. And when we multiply this out, when we multiply a binomial type term by another binomial term, how many terms do we generate? 4, right? We have all the various terms there. So here's those 4 terms written out. And then I rewrite it in a different arrangement where I do some factoring. And it turns out that 2 of the terms aren't influenced by the switching action of our 2 underlying signum functions. In other words, if I have the 2-sided spectrum in here, there's no switching action, whereas this one, there is switching action because there's the sign change that occurs right in the middle of the upper and lower sidebands. Likewise, that one occurs in that band, and then this one, oops. That one doesn't. So those groupings are what leads to this second rewrite. I'll just say blue and red. So the lower section is not impacted by the switching, and then the first 2 subterms are impacted by the switching. So
question.
yeah.
So without looking at the graph, I mean, how do you apply this by just looking at the equation? And figure out
How do I apply this?
to remove this the signum function from the last part of review, rewrite 2?
Okay. You don't want me to look at the graph. Well, I can look at it the other way, and I can say, okay, I think really what you want to know is, of the first 4 terms, which ones are not impacted? Well, that one, right? Because that's the spectrum shifted up to FC, and then the F plus FC has the switching action at minus FC. So those don't interact. And then the other one that's of that bent would be this one. It's where they're at opposite locations. The spectrum sits here, the switching sits over here, and vice versa. Not affected, right. So those become that last term. That becomes this. And then the other 2 are that. So that green one, in fact, is just double sideband. The only difference is it's got the 1/4 rather than 1/2. So that's original double sideband. And then if you go look at what these other terms are doing, this one and this one, they are splitting right down between the upper and lower sidebands, either at the positive or the negative frequency. And that is the action of the Hilbert transform filter, because the Hilbert transform filter is the signum function switching right at DC, but now we're having it switch at plus or minus FC. So we get the Hilbert transform gets involved with that, and that leads to this term right here. Let me put that together. Rather than a cosine, we have a sine in the time domain double sideband has the cosine, and then we have the Hilbert transform. And this effectively was like that property, the Hilbert transform, right? Or it's similar to that property, the Hilbert transform. It's Hilbert transforming the message plus the cosine wave. I'm trying to be a little bit faster because I want to get moving to what we need for the lab. But at any rate, this is what it comes down to. So if you have the plus sign here, then you get the lower single sideband. If you have the minus sign, then you get the upper single sideband. And you're Hilbert transforming and then multiplying by sine, or you're Hilbert, you're not Hilbert transforming and multiplying by cosine. So this is, like I said, it's known as a phase shift modulator, and this is the block diagram of it. So it says the upper path is double sideband, and then the lower path is the other term with the Hilbert transform. So this is m hat of t, and then that, this block diagram directly implements these equations. One of the things I guess I feel like I should explain to you that actually is very comforting and makes life easier is in comm systems, block diagrams are used a lot. And block diagrams explain what's going on, and usually if you start with a block diagram, you can then write out the math. If you write out the math, you can create a block diagram. So depending upon what learning mode you're in, if I'm developing a new system, I'll write out the math and then I'll draw the block diagram to make the picture view of what it is. If you're new to the problem, you might say, I want to see the block diagram first because I want to visualize what's going on, and then I'll try to write the equations out from the block diagram and see if I agree with the math that the original author did. What do you think about that idea? Because I'm really big when I mentor design teams on draw me a block diagram of what it is you're building. I just don't want to see the math or words. I want to see a picture view of how the system is working. Signal flows from left to right, and it goes through different operations. So that's phase shift modulator. Demodulating double sideband is very, very easy. We can use a coherent demodulator. We can just multiply by cosine 2 pi fct. The scaling factor is just a fudge factor to make things come out looking nice. So this is arbitrary, but this just makes nice numbers at the end. You've all had electronics. Is the gain of the amplifier 1, 2, 5, 10? I mean, you just pick a convenient value. But actually in electronics, you pick a value that makes you stay within that dynamic range of the device. You've certainly played enough with devices to know that if you drive things too hard, what happens?
It smells like burnt plastic.
Well, that or the clips, right? You look on the scope and you say, my sinusoid is, pardon me?
Like on the map, there's voltage trails, and if you input a signal that's too large and have too high of a gain, then it just goes to a high frequency DC.
Yeah, or clips. I mean, it's hitting the rail. The electronics people call that the rail, right? It hits the rail of the supply.
Like a layman.
Yeah. Do you like the term rail? I like it.
I think that sounds cool.
Yeah. It's not building a railroad either,
It's the
but.
coolest kind of gun. Railgun.
Oh, okay. Well, you're thinking a little bit more abstractly, but engineers like to think abstractly, so I'm fine with it.
I mean, I personally think CS people do it better. They're the ones who have all the funny names for like commands and OSs and all those
Yeah,
different
yeah.
packages. We need
We're
to-
pretty good at it, though. Don't think that they have the upper hand on us. They only have software. We've got software and hardware. What?
We have Wiener's theorem.
Okay. Yeah, and I have Wiener filter theory in my classes that I
Wiener
teach.
filter.
Norbert Wiener, he's the
Is it not Wiener?
inventor. No, it's Wiener.
All right.
Yeah, I'm fine with it. If you're snickering because of thoughts in your brain, you just keep them to yourself.
I'm not saying anything.
Call them hot dogs then if you want to.
Oh yeah, hot dog theorem.
At any rate, so if we carry out the analysis of the demodulator, we would look from our phase shift modulator result, we're just going to put in the received signal. So this is received. That's the RX signal. It matches the transmitted signal for this simple channel, multiplied by our coherent carrier, carry out the math, and use our trig identities. Notice how we get to use trig identities here. And then we get to ponder what we have, because our block diagram says what? We multiply and then we low-pass filter. So whenever you see in a comm system block diagram a low-pass filter and you don't see the cutoff frequency for it, you just have to assume that it means get rid of the high-frequency components, keep the low-frequency components. If I ask you to draw me a block diagram and I'll say, be specific, tell me the cutoff frequency, then you'll have to do that. So you'll say, cutoff frequency of this filter has to be at 10 kilohertz. If I make it lower than that, I'll remove some of my good signal. If I make it too high, I'll pass some of my double frequency terms or whatever.
There was actually something like that on the quiz where it said pick a cutoff, omega, or big delta.
Yeah.
Was it okay if you just chose any arbitrary number that was relatively close to the band?
Well, in general, if you wanted to be really precise, you would say something like, my pen to start working again.
Because I just chose a frequency that would really dampen the thing past 3 dB. So
You would pick the bandwidth of the filter could be anywhere in this interval, because it has to be above, say if this was W and this was 2FC minus W, if this was double sideband, it just has to be in that interval.
Okay.
For an ideal filter, if you're building a practical filter, you'd say, let's start cutting off a little bit above W so we can have that filter run down to lots of attenuation by the time it gets up to twice the carrier. And if the carrier is at 2 gigahertz and the bandwidth of the signal is at 1 megahertz, you've got from 1 megahertz to roughly 2 gigahertz to do that.
Cool, so I wasn't wrong with that. Awesome.
Okay, so carrying this out, we get the 4 terms again. Or 2 terms, No, we have 4. Let me look at this again. Yeah, we have 4 terms because I have the trig identity. We have cosine times cosine and sine times cosine. So we got these 4 terms. How do we make heads or tails out of it? Well, these are the ones the filter will remove. Ultimately, we haven't really gotten to that point because right now we're only at the pre-filter stage, but we can visualize that in our mind. So the terms that will come about after the filter are going to be these 2 drop down and survive. And if we're doing a coherent demodulator, we say, okay, what's actually going to come out of this is going to be m of t times cosine of theta, and if theta is nominally 0 for perfectly coherent demodulation, or 180 degrees like I had in the quiz, then what's going to happen? If, assuming theta is small, this term is going to be very small. That term is called crosstalk in a demodulator. A little bit of that leaks in, but it's the Hilbert transform of the signal, so it's not really all that noticeable. And I'm going to give you a demo of that in a second. Let's see, what else do I want to say? If there's frequency error in the system, then what's going to happen is the crosstalk term will still be small because of the Hilbert transform. And I guess, how do I want to say that? It's the Hilbert transform of the signal. But the message signal is going to get shifted in frequency by the cosine. So let's take a look at that. So here I created the single sideband signal using my function in Python, this function that I defined up here called analytic signal. And I took the message, the speech message now. I'm multiplying it an upsampled version of the signal. I'm multiplying it by the cosine, but this is the analytic signal. So xm up is, trying to see where am I creating xm up. I'm doing it right here. I create single sideband signal through the analytic signal generator with my speech message, and then I upsample it so I can put it up at a higher frequency carrier. And there's what the single sideband signal looks like, and I see it up on the carrier. Carrier's at 24 kilohertz, so what type of single sideband do I have, upper or lower? Well, if the carrier's at 24, that looks lower. It's below. Let's move that around. Let's go into here. Just verify that. I have to go up in here and make this upper. And then run it through the transmit function. And now it's the upper single sideband. So I've got upper single sideband, and now I walk through the same math we just looked at in the notes, and I'm going to do a coherent demod. So I'm going to multiply by my 24 kilohertz carrier exactly at 24 kilohertz. And then I low pass filtered that. So there's the spectrum before the low pass filter. So kind of like in a coherent demodulator, I've got the double frequency term, and then I've got the baseband term. And then I low pass filter it with a Butterworth filter just to get rid of the high frequency component. Listen to it.
Sockets in the wall, dull green.
Sounds perfect. Now I'm going to make the carrier not perfectly coherent. So I'm going to change this to 26. Spectrum looks kind of similar. Speech looks kind of similar.
Sockets in the wall, dull green. The child crawls into the dense grass. Bronze fan work, all fan work. Tiny.
So this is different than what double sideband sounded like with an imperfect coherent carrier. In the double sideband case, remember the math showed that we got an upshift in the frequency of the message and a downshift, and then they were superimposed. So we heard a pitch shift up and a pitch shift down combined. With the single sideband, because we don't have that other sideband, we're only getting it shifted up or shifted down. So what you just heard was which shifted down, right?
Kind of, yeah, because it felt like you could still hear his like.
But it was very gravelly sounding. So I could either coherently demodulate with a different frequency, or I could switch to the other sideband. So let's just suppose I decide to receive the signal as a lower sideband. So there's my lower sideband signal, transmit it, lower single sideband, and then I'll demodulate with the same frequency error, 24600. And then I will do this. So what do you think is going to happen? Is it going to be still gravelly downshifted in pitch, or is it going to be upshifted?
You changed the frequency. Did you make it lower than the other one?
No, I left the coherent carrier as the same value, but now I'm demodulating the opposite sideband.
Sockets in the wall, dull green. The child crawled into the dense grass. Rise, fail where honest men work.
Can you rationalize that in your mind?
Yeah. And the bottom pushes it over, and the top pushes it over.
Yeah, if we put the carrier at 24,600, it's supposed to be at 24,000. So 24,600 was moving up right over the top of the upper sideband message, so it effectively made the frequency difference smaller, so it was like lowering the pitch. And then in the case of the lower sideband, we're further away from it, so that meant that the pitch shifted up. You'd have to study the math. This notebook is available. You can play with it if you want to and listen to it. So single sideband speech can be received in that fashion. If we were doing data demodulation, we'd still be hosed up. We wouldn't be able to get data bits back without a coherent carrier. We're still going to have scrambled bits. So it doesn't solve that problem. But one of the things single sideband does alleviate is it sounds a little bit nicer if you have to manually adjust the carrier frequency. And I'm going to move into that shortly when I look at carrier reinsertion, how a single sideband receiver can actually function without having a coherent carrier at all and using an envelope detector. It's kind of a simpler technique. So this little section is called using carrier reinsertion and envelope detection. And this works somewhat similarly. It works using an analytic signal approach, and it's kind of DSP oriented as well. First, I have to look at some of the math behind it. This is a slightly different angle on it rather than using an analytic signal, but this is still the idea of envelope detection. Can we demodulate by adding a carrier rather than multiplying it? So we're just going to try to get the carrier frequency close and then use an envelope detector after we add carrier in rather than multiply. And in electronics, I'd venture to say it's easier to add a signal to a signal path. An op-amp can be used as a summer, for example, or a power combiner at RF frequencies, whereas a multiplier is a little bit more complicated hardware. So we add the carrier in, and if we just assume initially it is coherent, so it's actually a cosine. So in our expression for what's going to drive the envelope detector, this is the inserted carrier. And when we add that in, what we can do now is we can proceed to find the envelope of this signal, which is going to be finding the complex envelope, which is like dealing with our analytic signal. And I'm looking at the clock thinking I'm going to run out of time. This is a really important idea, and it's going to take more than 3 minutes to go through it. So should I jump ahead and show you frequency translation and mixing for a couple of seconds? Because it's a simple enough concept. I won't be able to run the last demo, but it works just fine. And I'll show it to you next time. This happens to have a lot of development behind it. Vestigial sideband I don't cover anymore. This was used in analog TV. Digital or HD TV uses a form of vestigial sideband still, but it's for digital signals rather than analog.
So discrete.
Well, the information is now bits rather than signal waveform samples, but they still use vestigial to try to make the bandwidth less. Here's actually a picture of it right here. In a vestigial sideband system, this was the old analog TV. Rather than totally throwing away one of the two sidebands, they left what they call a vestige. That's where the vestigial comes from. In this case, the lower sideband. But this is NTSC TV, which is gone. It's off the planet. Maybe you can talk about that since you worked at Ampex probably when they were still doing analog TV. Were you part of it? Last century? No? Okay. It carried us through the times, though. So frequency translation and mixing. When you start looking at superheterodyne receivers, which is what this gets into, this basic principle is used. And the idea is we have a signal at F1, and we want to move it to F2. So we just multiply by a local oscillator signal, and we just need to make that local oscillator frequency be one of two frequencies. It can be omega 1 plus omega 2 or omega 1 minus omega 2. And it's just all comes down to a trig identity. And it's actually one of the reasons why I say trigonometry is so important to communications. When I took trig in high school, I'm like, trig identities, not too excited. But if I think about how you can multiply one signal by a cosine and you apply the trig identity of shifting its frequency, so that's what we're talking about here. If we put in double sideband and we multiply by this local oscillator at this frequency, what's going to happen is, see, when we add and subtract, remember, cosine x, cosine y, it's 1/2 cosine x plus y plus 1/2 cosine x minus y. So that's what we're getting out here. We're getting the difference ends up being, in this case, cosine omega 2. So we have moved it to a new frequency, and the sum is shifted up higher in frequency. And then you just need to put a bandpass filter out there to keep the signal that you want. So that's what the bandpass filter is doing. And I know I'm out of time, so I'll just show you. This moves then into superheterodyne. This is an AM radio superheterodyne concept. This is what Armstrong pioneered back at past in like the 1912 or 1918, somewhere in that time frame is when superheterodyne principle was discovered, that I could take a signal at an RF frequency and then I could move it to a new frequency, the frequency translation idea, with a mixer. And this is a block diagram of how that works out. We then have this frequency chart that shows sort of the receiver frequency plan. If we have a desired signal at 560, we put our local oscillator and we want to move it to 455 kilohertz. So this is where we want to move it to. We want to move 560 to 455. We can choose to put our local oscillator at 1015, which is 455 kilohertz above 560. So what? So the difference is at 455. And then we'll have a sum frequency. We'll have a 560 plus 1015, which will move it up higher in frequency. But once we move it, then we just bandpass filter, which is right here, and we get our signal back. I guess I drew that error in the wrong place, because this talks about a superheterodyne issue, and that is something called the image. So that's the 455, though. And the image just tells us that if we put another signal at 455 above the local oscillator, it will form a difference relative to 1015 that also comes down to 455. So how do you avoid the image? You put a RF bandpass filter out in front. That's what this guy is to represent, to make sure you can reject the image. And that's why you've got this tunable filter out in front, to remove the potential for an image. And there's a lot of techniques around that. We'll probably talk about that more, and it'll be on a quiz or something too, and it'll show up in the exam too at some point. And then in the lab, you also, there's 2 receiver boards that I've designed, and Professor T. Camp implemented my breadboards into, my RF breadboards into PCBs. But the second receiver, one receiver does FM with a single conversion, and then this is a double conversion idea that is more typical of a narrowband receiver. So this is also implemented exactly in this fashion, and exactly for receiving weather channel number 4 at 162.475 megahertz, which is over in Manitou Springs. That's our nearest weather channel operated by NOAA. Has anybody ever listened to the Weather Channel? Okay, you will in the lab. You'll be fixing the right local oscillator frequency, and then you'll be putting the antenna on the radio, and you'll be hearing weather, and you'll tune in FM broadcast with the other receiver. So you'll have fun with that. I like it a lot. You get to probe things. You get to learn about frequency translation and mixing. I'm way out of time. Wish I could have had more time, but we'll get back on top of this next Tuesday. So you've got 2 pretty simple problems to work on with analytic signals, getting you more prepared and moving towards the exam. I should get the old exams up there and posted. Hopefully I'll get that done tonight. keep thinking about where does the time go, because tomorrow I get to come in and say, I'm going to get a lot done today on the stuff I want to do. Oh, I have Capstone Design to sit through 3 hours of talks tomorrow morning. So, you know, there's always stuff to take my time. Today was,
Some popcorn.
yeah,
Throw it at 'em.
I don't know if I'll do that. But I had a reasonable day interviewing. I got to have a breakfast at the Omelette Parlor, and I got to go to Marigold's for lunch. And
sounds nice.
those are both pretty nice restaurants by me.